Hi, everybody. We're back with 3.3. This is going to be about some other cosmic bodies and oddities. And you may notice that I have a helper here today. She's going to help talk about a couple of the different things we're going to go over. So, just so you are aware, we're going to look at some of the weird things that are out there that we haven't covered a lot and we aren't going to spend a whole lot of time on. So these slides will provide a brief introduction to our cosmic oddities, very brief. Some of these exist, some of them don't, some of them might. And there are more out there that will not be covered, just so you're aware. So, Anna, can you introduce yourself?
My name is Anna. I'm 6 years old. I'm in kindergarten. Yeah,
and this is my daughter. So, can you tell us what you know about black holes?
Black holes are stars. If they're big enough, if they do another explosion, then they turn into the black hole.
And what happens in a black hole?
They suck light and stuff into them.
Sure. So I'll go over a couple other things. She's right. So as we talked about in the last chapter, if a star is big enough, it can actually implode to the point where it turns into a black hole. It's an area in space where gravity is so strong that light, matter, electromagnetic radiation, nothing can escape. And it's generally the result of a massive star dying. Supermassive black holes exist in the center of galaxies, and we'll talk about how they relate to something called a quasar later on. There's a boundary of no escape called the event horizon, and things that happen here get pretty weird. We don't really know what happens in the event horizon because it can't be known. Information can't get back out of the event horizon. So to an observer, if we sent a clock towards a black hole, time would move slower and slower. That's called time dilation. The object falling in would appear to move slower and slower until it went to an infinitely slow speed. But to the object falling in, time would appear normal. The clock would look like it's ticking normally. Now, if we were to fall in, we would be spaghettified, and that is not a good thing. That means that if we went in feet first, we would be stretched out an atom thick and turned into one long piece of spaghetti. And here's a little picture of some different parts that you can look at on the slides. It has all the different parts to it. Now, there's also something that could possibly exist that is the opposite of a black hole. Anna, what are those called?
White holes.
Oh, can you tell us anything about white holes?
So white holes do all the opposite of black holes. Like they spit the white out. They spit out the white. They spit out light. But the black hole gets it in, but it spits it out. It's like it's the other side.
Right. That's the idea. Mathematically, it's the opposite of a black hole. Objects cannot enter, they can only come out. So it is described as time reversal, where time would actually look like it's going backwards. The event horizon is exactly the opposite. Nothing can go into it at all. Nothing would be pulled in. Everything would be pushed out. They're thought to be very short-lived, like they'd only live for a little while and they'd exist and they would be gone. Perhaps it's the death of a black hole, where everything that was swallowed pops back out again. Perhaps it's a replay of the formation of a black hole. And here is an image of what they think it could be like. Now, there's one other type of hole we're going to talk about. What is this one called, Anna?
A wormhole.
Oh, yes, a wormhole. And what happens in a wormhole?
In a wormhole, it likes to teleport you through time.
Yeah, it's kind of a weird thing. It can teleport you through time and space. They're hypothetical. We don't know if they exist, but they're a connection between 2 points in space via a tunnel. It's kind of like if you would take a piece of paper and you would fold it up and you would put a point on two different spots, and all of a sudden, when you fold the paper, they could touch each other. You've basically warped space and brought those 2 points into contact. It's a possibility that was discovered by Einstein and Rosen in 1935. The research started from black hole math, and the wormhole could connect black holes and white holes, possibly. So maybe something goes in one and comes out the other. The problem we know is that nothing can go into a white hole and nothing can leave a black hole, so it makes it kind of questionable if they're related. Physicists worked out the math in the 1970s of a traversable wormhole, meaning something that could go in and come back out, but you would need exotic matter with negative mass, which we don't have yet. In theory, it could be like a time machine. Like Anna said, it could actually allow you to move around in time. The other possibility to stabilize a wormhole is negative energy, and that does exist. We have negative energy, we don't have negative mass. And it's possible that the solution lies in the quantum realm in something called quantum foam. Okay, so here's a little picture of, the idea of a wormhole and what it might look like. Okay, so the next slide is going to be on something called neutron stars, magnetars, and pulsars. So all of these are a type of neutron star, just so you're aware. Magnetars and pulsars are special cases. So what this is a collapsed core of a massive supergiant star, but not quite big enough to turn into a black hole. They wind up being very, very small and very, very dense. So they're only miles in diameter, so maybe only 5, 6, 7 miles across. And they start off very hot, but they cool off over time. They are composed only of neutrons. That's why they're called a neutron star. The protons and electrons have been combined to produce these neutrons. They've been smushed back together, so they become a neutral particle. They're extremely dense, so dense that if you took a matchbox size, so just a little chunk of this, it would be the weight of an entire island like Manhattan Island. That's how densely packed this stuff is. They could rotate up to several hundred times per second. And if they do that and they emit electromagnetic radiation, they're called a pulsar. The fastest pulsars are spinning 716 times per second. Neutron stars with huge magnetic fields, like 1,000 times stronger than normal, would be called a magnetar. So they're both different versions of neutron stars. And this is what a magnetar would look like. Okay, quasars are luminous active galactic nucleuses. And that is shortened up with the letters AGN. The term means quasi-stellar radio source. Now, these things are strange, and they are very, very old. Radio wave emissions are given off by a supermassive black hole found within the quasars. So these quasars have supermassive black holes in the center. But while we found a lot of them, the closest one is 600 million light years away. So what that tells us is that these are probably very, very young galaxies that were just starting. And it's taken 600 million years for the light to get to us. So those things probably are not looking the same. They generally glow very, very brightly, and that's how we can see them. The mass is over 1 billion times that of our sun, and the total energy output can be 1,000 times greater than our entire galaxy. So here's a picture. Now these are very, very bright, and they're very, very far away. We don't have any of them nearby because they are basically young galaxies, and the ones we have nearby are older. Okay, so here we have a little summary of an exoplanet and a rogue planet. So exoplanets are all the planets beyond our solar system, and we didn't start actually seeing them until the 1990s because they're so small that we can't really see them with direct imaging. They're really hard to see that way unless they're really big and really close. Most are found by the dimming of a star or monitoring the spectrum for redshift. So we can see a star dim as the sun or the planet passes between us and the star, and it dims a little bit. Some of them have been found through gravitational lensing, where gravity kind of warps the visible field around it. And a lot have been found that are ranging from Mars to Jupiter size. So some that are a little smaller than Earth and some that are quite a bit bigger. The closest that we know of is 4 light years away. That's also where the closest star is to us. So they have their own planetary system. Now, rogue planets are all exoplanets, but these are ones that are free floating. They're not actually in orbit around a star. They may have been ejected from their star system. Some form on their own. Some might have been part of a different system and just, like I said, got ejected away. There may be billions to trillions of them in the Milky Way galaxy. One nearby has an actual accretion disk, which means it formed and it has an actual disk, kind of like a mini solar system almost, like a little mini planetary system. They're generally very cold, but some can have a little bit of heat to them. Some of them may have been working their way towards a star and they were too small, like a brown dwarf. And they might even have an atmosphere, even though they're not near a star. So here are some different exoplanets that have been found. And this is actually a rogue planet that they have seen. It looks kind of like Jupiter. Okay, and we have dark energy and dark matter. And I'm going to zip through this one kind of quickly. Dark energy makes up about 68% of the universe, and dark matter makes up about 27%. That means the matter that we know about makes up only 5%. That means there's a lot of stuff out there, a lot of mass energy that we can't see. It might be the energy of empty space itself. Dark energy might be the result of quantum fluctuations. It is not matter. or antimatter, or dark clouds of matter. So when they talk about dark matter, it's not just dark matter. It is stuff we can't detect. It doesn't interact with an electromagnetic field, so we can't see it very easily. And it could be made up of exotic particles like axions or weakly interacting massive particles, WIMPs. Kind of an interesting name. Tongue twister for me, apparently. So here is a little summary of dark energy versus dark matter. And last but not least, things that could exist, but we don't know for sure. Aliens? Maybe. Maybe they're aliens. Maybe they're the cute and cuddly type. Maybe they're just kind of that humanoid type. Maybe they're not so nice. Maybe they're really not nice at all. So that summarizes other things that could be out there. And there are many other things that are out there or that could be out there that we don't know about.